The first part of Lesson 10 is a review of quadratic equations. And just think about our standard form, our standard quadratic form. Ax squared plus bx plus c is equal to 0. And we could think of a quadratic polynomial just as an example. Let's do x squared minus 5x plus 6. We could factor this one into two binomials pretty easily. We don't have to use the quadratic formula. We could just say x minus 3 times x minus 2. And we would say that the zeros for that polynomial are 3 and 2. The zeros equal 3 and 2. Those are the values that would make that polynomial equal to 0. If we substituted a 3 in, whether it's factored or not, it's going to equal 0. And if we substitute a 2 in, it's also equal to 0. Now, the only difference between a polynomial like that and a quadratic equation is you just put a equals to 0 in front of it. X squared minus 5x plus 6 equals 0. That is a quadratic equation. And again, we can just write this x minus 3 times x minus 2 is equal to 0. And we call the solutions for that, the values that would make the left side equal to 0, we call those roots. They're just different words. They mean the same thing, basically, or they give us the same value. It's still 3 and 2 are the roots. But when we're dealing with an equation, when it's set equal to 0, that polynomial is set equal to 0, we call the solutions to that equation the roots. When it's just a polynomial by itself, we call the values that would make it 0, we call those zeros. The only thing to think about here is that when we say find the roots of this, we know that we're talking about an equation. When it says find the zeros, we know we're just talking about a quadratic polynomial. That's the only difference there. Now, a polynomial function, remember functions, you're comparing an output value and an input value. For every input value, there will be one and only one output value, or we'll just say y value, and we can use the same relationship here, x squared minus 5x plus 6. So now we have a quadratic function. Y is a function of x, or depends on x. And we could factor that out again. Y is equal to x minus 3 times x minus 2. And the whole purpose of functions is really to graph them on a Cartesian coordinate system. And René Descartes developed the Cartesian coordinate system. He basically set the groundwork for what Newton did with the Cartesian coordinate system. Remember that when we're talking about calculus, we're talking about instantaneous changes in rates. Really, really, really small changes at a certain instant in time. A rate compares two values. So that's what a function is, right? It's a comparison of two values, an input and an output, a dependent and an independent variable. We don't call the solutions here, we don't call them zeros, we don't call them roots, we call them Xintercepts. The Xintercepts equal 3 and 2. And just think about that. If we graph this function, when x is equal to 3, y equals 0, so that would be 3, 0, a point right there. When x equals 2, y equals 0, so that would be this point right here. Those are Xintercepts. Now recall from Algebra 2 and Advanced Mathematics the basic polynomial or parabola function, y equals x squared. And remember, if you graph that, it just looks like this. It has a bottom, basically, or a vertex at the origin, because when x equals 0, y equals 0, that's the lowest point on it. Every place else is above that. Now maybe you remember this. When you want to shift that parabola anywhere on the coordinate plane, you just use a point h, comma, k, and you represent that in the quadratic equation, or the parabola equation, as y minus k is equal to x minus h squared. And you can rearrange that. Y is equal to x minus h squared plus k. So if you get a parabola or a quadratic equation, in other words, in that form right there, y equals x minus h squared plus k, you can determine where the vertex is located. And then that will help you graph the function. For example, the function we've been using, y equals x squared minus 5x plus 6, we know where the x-intercepts are, but we don't know where the vertex is. So we could go ahead and figure that out by doing a completing the square on y equals x squared minus 5x plus 6. Now maybe remember doing this. What you do is take half of that negative 5, which would be negative 2.5, or we'll just call it negative 5 halves. You square that, so that would be 25 over 4. And we add that inside the parentheses and put it on the outside as well, so we'll just have to make it a negative 25 over 4 on the outside of the parentheses. Because we can't just add a number on the right side of the equal sign. We have to make them cancel out. Now we can complete the square and say x minus 5 halves squared plus 6 minus 25 over 4. Well, that'd be 24 over 4 minus 25 over 4 would be minus a 1/4. Our vertex is at h, comma, k. So what we have to do then is just think of h, x minus 5 halves, so 5 halves, and then k is minus 1/4. Now we go back and we look and see what we have. Go to the right 2.5 basically and down 1/4. So something like that. And we could just go ahead and graph the parabola through like that. So that is the graph, or at least an estimate of the graph of y equals x squared minus 5x plus 6 for that. That's that function. Remember this formula here. Y equals x minus h squared plus k, and that h comma k is the vertex for a parabola. If you've been given a quadratic polynomial function in the form like we had above there, y equals x squared minus 5x plus 6, and you wanted to graph that, you have to use completing the square to get it in that form, y equals x minus h squared plus k. That allows you to find the vertex. Then you can just find one other point on it that lies on that parabola and make a sketch of the parabola. So the values of x that make that quadratic part, or the polynomial part of this quadratic relationship, equal to 0, they're called zeros when it's just a polynomial. They're called roots when it's an equation set equal to 0. They're called x-intercepts when it's a function. Different names for the same thing depending on whether you're dealing with just a polynomial, an equation, or a function. Now you might see some problems like this where it'll say factor over the set of complex numbers. And so this is just a quadratic polynomial, and what we'll need to do then is find the zeros. We won't call them roots or x-intercepts, we'll call them zeros since it's just the polynomial function, or not function, but just the polynomial by itself. So let's go ahead and use the quadratic formula, find the zeros, and then we can factor that into two binomials once we find the zeros. So we'll have negative 2 plus or minus the square root of 2 squared, or 4, minus 4 times a is 3 times c is 1, or we'll just leave it as 3, all over 2 times a, which would be 6. And then that will equal negative 2 plus or minus the square root of 4 minus 12 would be a negative 8, all over 6. And I can simplify some more to minus 2 plus or minus a negative 4. We can take that out from underneath the radical sign and get a 2 times the square root of 2i all over 6. And then that will simplify to negative 1 plus or minus the square root of 2i over 3. So we have two zeros here, and we can write this as zeros equal minus 1/3. Remember, when you write a complex number, you should have a real part and an imaginary part. Minus 1/3 plus or minus the square root of 2/3 I. And then to factor it, we'll have x plus 1/3 minus the square root of 2/3 I times x plus 1/3 plus the square root of 2/3 I. That would be the factored form of that expression. When it says factor over the set of complex numbers, all that means is you'll use the quadratic formula to find your zeros, and once you find your zeros, those will be complex numbers. They're giving you a hint there that they'll be complex numbers. Just don't forget, though, when you find zeros and you want to put those back in to make a factored expression, you do the opposites of them in the expression, because minus 1/3 plus the square root of 2/3 I, if you substitute that into that factored expression, that's what makes it equal to 0. That makes the factored expression 0. And 7. Now, something else to consider here is that we need to put a 3 as a factor in front of this factored expression. Think about what the quadratic formula is. The quadratic formula is a way to find the zeros of a quadratic function. And if you recall, you use the completing the square method to solve for the zeros of the ax squared plus bx plus c equals 0 standard quadratic function. Your first step in that is to factor that a coefficient out. So if a is anything but 1, in this case it's a 3, the 3 and the 3x squared there, you just have to think that, well, the zeros that I just found here, those are factored out, or that's when I have factored that 3 out. All the quadratic function is a shortcut for the completing the square method. So if you see a problem like this again where you have to factor over the set of complex numbers, find the zeros using the quadratic formula, then go back in when you're done and you have your two binomials, put that factor of x squared, if it's something other than 1, make sure and include that back in. Let's do another problem. Look at B. I want you to graph that quadratic polynomial function there. H of x equals 2x squared minus 6x plus 4. So this will be similar to what we did in our example. We need to use completing the square to get it in that standard form of y is equal to x minus h squared plus k. Once we do that, we know that h comma k is the vertex, or like the bottom point of the parabola. We call it the bottom if it opens upward like that. If it's opening downward like this, then it would obviously, the vertex would be the top of that parabolic function when it was graphed. So let's go ahead and do completing the square on this. We'll have h of x, instead of y, we have h of x is equal to 2. Remember, you can't have a coefficient other than 1 in front of the x squared term when you do completing the square. So we have to factor a 2 out, and we'll have x squared minus 3x, and then close parentheses off and put the plus 4 out to the outside there. Half of negative 3 would be a negative 3 halves. Square that would be a positive 9 over 4. And so we have to put a negative 9 over 4 on the outside. But be careful. Don't forget about this 2 right here. We have to watch out for that 2. We have to say 9/4 times 2, or negative 9/2 on the outside. Because really what we've done there is add a 2 times positive 9/4, or a positive 9/2. So on the outside we have to say negative 9/2. Be careful about that when you do these problems. Now we can go ahead and complete the square. We'll have h of x is equal to 2 times x minus 3/2 squared, and then we'll have minus 9/2 plus 4, or plus 8 over 2. Minus 9 over 2 plus 8 over 2 would just be minus 1 over 2. And now we can figure out our vertex. It's going to be at h comma k, so we'll have x minus h minus 3/2, so h is 3/2, and then plus k, so k is a negative half. 3/2 and negative half, that's our vertex. Let's just go ahead and make a Cartesian coordinate system here, and we'll put some tick marks down. Go to the right 1.5 and down 1/2, and there's our vertex. Now that coefficient of 2 in front of our factored binomial, that's a positive 2, so that tells us that the parabola will open upwards. If it was a negative number, that would tell us it would open downwards. The larger that number is compared to 1, the narrower the parabola is. The smaller of a fraction it is, less than 1, like 1 over 2, 1 over 4, 1 over 8, the smaller that fraction is, the wider the parabola will be. Now we can always find the y-intercept where it crosses the y-axis by just looking back at our original function, h of x equals 2x squared minus 6x plus 4. Look at that. Substitute when x equals 0, or substitute x equals 0 in for that. H of 0 would equal 2 times 0 minus 6 times 0 plus 4. H of 0 equals 4. That is our y-intercept. So we can put a dot there at 0, 4. And parabolas are symmetric, so if we sketch 1/2 of it, the other half will look identical to it. You don't have to draw it, but at the vertex, parabolas always have what's called an axis of symmetry that goes through it. We find our vertex using the completing the square method there, and then we can find the y-intercept, just find one more point to help us graph the shape of that parabola. And as you can see, that's a fairly narrow looking parabola. When you work on calculus, doing parabolas is a very important part of that work, and especially when you're learning about differentials, which we'll learn about fairly soon. Being able to work with and manipulate parabolic functions is going to be a very important skill to have. Here's something new that you really haven't done before, and this says find the quadratic function whose graph has x-intercepts at 1 and 4 and a y-intercept at -3. Well, let's just think about this. If we had this function, it has x-intercepts at 1 and 4, so we know we could write this much at least. X minus 1 times x minus 4. Because the x-intercepts would be 1 and 4. That would make that equal to 0. That would make y equal to 0. Now it has a y-intercept at -3. So what we need to do here is just put a c out in front. C standing for constant. There's going to be some constant that these two binomials will be multiplied by. So that's how you do problems like this. When it says find the quadratic function and it gives you the x-intercepts, just set up two binomials related to those intercepts and just say y equals that. Then just put a c for constant in front of it. Now what we'll do is just say y over c and expand out those two binomials. Y over c is equal to x squared minus 5x plus 4. Now when y is equal to negative 3, the x's equal 0, right? Because that's when you have a y-intercept. And we can solve for c at that time when x is equal to 0. So we would just say minus 3 over c is equal to 0 squared minus 5 times 0 plus 4. Minus 3 is equal to, or minus 3 over c is equal to 4. Minus 3 is equal to 4c. So c is equal to minus 3/4. That's what that constant term is. Therefore, the equation ends up being y is equal to the constant negative 3/4 times x minus 1 times x minus 4. Now we don't really want to leave that in the form of binomials like that, so let's just go ahead and expand this out. We'd have y is equal to minus 3/4 times x squared minus 5x plus 4. And go ahead and multiply through. We'd have y is equal to negative 3/4 x squared plus, because we have a negative times a negative, plus 15/4 times x, and then minus 3/4 times 4 would be a negative 3. And that's what we should expect, right? Because in that function right there, when x is 0, y is negative 3. That would be our y-intercept, which is what we were given. If we substitute x equals 1 into that equation or function that we have at the bottom there, we'd have a minus 3/4 plus a 15/4 would be 12/4, or 3 minus 3 is 0, which is our x-intercept. And then we would see that 4 is also an x-intercept. If we wanted to graph this relationship, though, we would still need to figure out the vertex, and we'd have to do completing the square on the function that we have solved for here. Do completing the square on that to get it in the y equals x minus h squared plus k formula, or format, and then we could figure out the vertex. So on a problem like this, when they've given you the x and the y intercepts, you just set it up as knowing what the two binomials are. You can figure out the two binomials and just say y equals a constant times those two binomials, and it's very easy to solve for that constant. Then expand the binomials out, multiplying them by whatever that constant equals to get your quadratic polynomial function form. Part B of this lesson is on the remainder theorem. Remember, axioms and postulates are things that we accept without proof. Theorems, we use deductive reasoning to get theorems. Theorems are also rules that we can accept as true, but they have to be proven true. We proved the remainder theorem in advanced mathematics, so we won't really get into proving it here. Just remember that if c is a 0 of a polynomial, then dividing that polynomial by x minus c will give a remainder of 0. Let's look at a practice problem and apply the remainder theorem. Let's find out if 2 is a 0 of x cubed minus 3x plus 4. Now, of course, we could just substitute 2 in there and see if that makes that equal to 0. Let's just use our remainder theorem anyway, and that means if we divide this by x minus 2, so we'll have long division format here, x minus 2, and then our division symbol there, x cubed plus 0x squared, since we don't have an x squared term, minus 3x plus 4. If the remainder of all this is equal to 0, then we know that 2 is a 0. So first we need to put an x squared here. X squared times x is x cubed, and then minus a 2x squared. Subtract 0 minus a negative, that would be plus 2x squared. Bring down a negative 3x. And then we need to get rid of the 2x squared, so we'd be multiplying up here by 2x. 2x times x is 2x squared. 2x times negative 2 is minus 4x. So we subtract minus 3 minus a negative or plus 4x would just give us x plus 4. We need to get rid of that x, so we're just multiplying by 1. X minus 2 goes there. 4 minus a negative 2 is 4 plus 2, or 6. Our remainder is not 0, so our answer basically is no. And we always want to answer the question being asked. The question is 2 a 0? No, it's not. Something else I didn't write down about the remainder theorem is that if it's not a 0, then the remainder equals the value of that polynomial when x equals c, or in this case x equals 2. But we could substitute in there real quick and we'd see 2 cubed is 8, minus 3 times 2 would be minus 6, so that would be 8 minus 6 is 2, plus 4 is 6. So that remainder does equal the value of that polynomial when x equaled 2. If c is a 0 of a polynomial, then dividing the polynomial by x minus c will give a remainder of 0. Now you probably remember in advanced mathematics something called synthetic division, and that's part C of this lesson. And you probably remember it because it was just incredibly easy to find a 0 of a function or to divide a polynomial compared to using the long division format. Let's just review synthetic division here using the problem that we had in A. If we're dividing x cubed minus 3x plus 4, if we're going to divide that by x minus 2, we put a 2 kind of like in a little box on the corner, and then we write down all of the coefficients that we're dealing with. We'd have a 1, a 0, a negative 3, and a 4. Just remember the pattern on this. What we do is bring down the first coefficient, that 1, multiply it by the 2. 2 times 1 is 2, and you put that here. Add the 0 and the 2 together, and you get a 2. Now multiply that 2 by the 2 in the box. 2 times 2 is 4. Put that here. Add 4 and negative 3 together. You get a 1. Multiply by the 2 in the box. 1 times 2 is 2. Add that here. 4 plus 2 is 6. That's your remainder. Now, of course, that's not exactly the remainder. The remainder is 6 over x minus 2. And if we wanted to write out the whole quotient, we'd say x squared plus 2x plus 1 plus 6 over x minus 2. Basically, that last number that we get is the numerator of the remainder. Synthetic division, we use that to find zeros of polynomial functions that are very big and complex. When we're dealing with a polynomial function, though, we call them Xintercepts, because every time we find a 0, a value that makes that function equal to 0, we're finding a place where it crosses the x-axis. Those are important locations because it helps us graph the shape of that polynomial. Let's use synthetic division to solve this problem here, this polynomial function. If h of x is equal to x to the 4th minus 3x cubed plus x squared minus 1, I want you to evaluate h of 2 and h of negative 1. So we could just substitute 2 in there, but we could use synthetic division, which should be quite a bit quicker to do that. The remainder of all of this will equal h of 2. So let's just go ahead and write down our coefficients. We put 2 in a little box and write down the coefficients of our polynomial. 1 minus 3, 1. There's no x term, so we need to keep up with that. Put a 0 there and a minus 1 at the end. And so now we just go through and bring down a 1. You always bring down that first coefficient. Multiply it by the 2. 2 times 1 is 2. Put that here. Add those together, you get a minus 1. and then a minus 2 would go here, and add those together, you get a minus 1 again. Minus 1 times 2 is minus 2. Add those together and you get a minus 2. Then multiply that by 2, you get a minus 4, which goes there, minus 5. So h of 2 is equal to negative 5. We can just box that. Now let's do h of minus 1. We just put a minus 1 in the box, have our same coefficients, 1, minus 3, 1, 0, and negative 1. Let's go ahead and work on this one. Bring down the first coefficient. You always do that. Multiply it by the negative 1, so you have a negative 1 here. Add those, get negative 4. Multiply by negative 1, that would be a positive 4. Add those and you get a 5. Multiplied by a negative 1 would be a minus 5. Adding those, you get a minus 5. Multiply by negative 1, you get a positive 5. Add those, that's a 4. h of negative 1 equals 4. Now, like I said, we could substitute in, for example, if we substituted a 2 in to h of x, we could solve, and we should get a negative 5. It's just a lot more mathematics to keep up with. We'd have 2 to the 4th minus 3 times 2 to the 3rd plus 2 squared minus 1. And then we'd have 16 minus 3 times 8 is a negative 24 plus 4 minus 1. 16 minus 24 would be a negative 8. And then 4 and a negative 1 is a positive 3. Minus 8 plus 3 equals negative 5. Get the same answer. We should get the same answer because that's what the remainder theorem does for us. Doing synthetic division just speeds up the process tremendously. It's a quick way to find x-intercepts. Knowing where the x-intercepts of a polynomial function are, that helps us graph the function. Let's go on now and learn a little bit more about evaluating polynomials. In Part D, we're talking about the rational root theorem. And you learn this in advanced mathematics. Basically, it says that if a polynomial has a rational zero, that means a ratio of integer values, right? If it's going to have a rational zero, then that number is going to be a fraction such that the zeros are going to be some factor of the constant term divided by some factor of the lead coefficient. There is no comparable theorem for finding irrational roots, but there is this method here that we can use to find rational roots. Let's go ahead and do a practice problem dealing with the rational root theorem. Have this function here, f of x equals x cubed minus x squared minus 3x plus 3. Find all the possible rational roots of that. Or I guess since it's a function, we could say all the possible rational x-intercepts. Then use synthetic division to find out which one of those really is a rational zero. So we'll have f of x equals x cubed minus x squared minus 3x plus 3. We think of our rational root theorem. It's all of the factors of the constant term. So that constant term is a 3 over the factors of the lead coefficient. The lead coefficient is 1. Now think about that constant term 3. What factors of that would equal 3? Well, we'd have 3 times 1. So 3 and 1 would work. We could have minus 3 times minus 1. Those two would work as well. Now the denominator, the lead coefficient, 1 works because 1 times 1 is 1, and then minus 1 times minus 1 would work as well. So 1 and minus 1 are some possible values there. So now what we have to do is look at what we have here and come up with all of the possible rational zeros. Just start with the 3 in the numerator. Divide that by 1 and you'd have 3. Divide it by negative 1 and you'd have negative 3. Then go to the 1. 1 divided by 1 would be positive 1. Divided by negative 1 would be negative 1. So that's usually what happens here. You'll have plus and minus of similar numbers. And then if you went to the negative 3, you'd kind of repeat again. So you don't have to repeat them. These are all of the possible rational roots right there. 3 and minus 3, plus and minus 1. Now go ahead and use synthetic division on all of those possible rational zeros to see which one really is a zero of that function. So what you do is just go ahead, we'll start with 3, put it in a box, then put down all of our coefficients for the polynomial. 1, minus 3, and positive 3. And go ahead and do synthetic division on that. If our remainder is 0, that tells us that the 3 is a root. So let's get started. We have a 1 there, multiply, put a 3 there, a 2 here, multiply by 3, we get 6, get a 3 there, a 9 here, a 12. So 3 is not one of the roots. It could have been, but that's what the rational root or zero theorem does for us. It tells us possible roots. It doesn't mean that they will. It just simplifies our work some. I mean, otherwise we wouldn't have any way of knowing. It would be really hard to guess on a polynomial like this what the zeros are. So let's go to a 1 now. Let's try that. And put our coefficients down. 1, minus 3, and 3. A 1 here, a 1 there, that'd be a 0 there. So that would be a 0 here. Minus 3 there, minus 3 here, a 0 there. So that means that 1 is a 0. So we'll put that up here. Now go to minus 3. See if that is a 0. Write out your coefficients. Bring a 1 down here. Minus 3 goes there. Minus 4 there. A 12 goes here. And a 9 there. And a negative 27 here. So we know that's not going to work. We can just go ahead and stop. And let's do negative 1. That's our last option, or our last possible root. 1, minus 3, and 3. Positive 1 was a 0, so maybe negative 1 will be as well. Bring a 1 down there, minus 1 goes here, minus 2 there, positive 2, minus 1 there, positive 1, that one's not going to be a root. So 1 is a 0 of that polynomial function. It's an x-intercept. So we use the rational root or zero theorem to help us find an x-intercept for this particular function. We found a rational x-intercept of 1. Now there are some irrational ones as well. Typically what happens is the highest order of that polynomial, that tells you how many possible zeros you might have. So we found one of them. That means there's still 2 more because we have x cubed. The other 2 must be irrational roots. Remember, what you're doing right now is building on a foundation. This foundation, as long as you know all of these foundational principles well, then that's going to make calculus, when we get to the calculus, that will make that easier. So make sure you know and understand the rational root theorem, the remainder theorem, and synthetic division. As always, a graphing calculator is a good tool for checking work, and we can use it to check our work and estimate the roots on this particular problem. First, we want to set y1 equal to x cubed minus x squared minus 3x plus 3, and then we want to set our window up appropriately. You should come up with a zoomed in window. It's good to be able to see, especially where the graph crosses the x-axis, because that's where our zeros are. That's the main thing we're concerned about. So we can see a 0 there, here, and here. Then we just follow our steps. We go to Calc, which is just hit the second key and the trace button up at the top, and then we hit number 2, 0, which is finding a 0, and we follow the directions. Remember, we just use our left arrow and our right arrow to move the cursor around. Move it to the left side of that 0 to find a left bound. Move it to the right side to find a right bound. Make a guess close to it, and you should come up with x equals minus 1.732051, x equals 1, and x equals a positive 1.73205008. If you remember, we said one of our rational zeros would be x equal to 1. That was our only rational zero. And there had to be two irrational ones. That's what the other two numbers that we see here are. Okay, well that's all for lesson 10.